Our speaker this week is Professor Zikui Liu from Pennsylvania State University. We've known each other for about 17 years. I met him when I was a postdoc. And he was still an old man even back then. He'll get me back later. When it comes to creative thinking about computational material science and the possibilities for what you can do in the design of materials, he falls kind of in the top 10 of at least my personal heroes in this space of material science, computational material science that is used to engineer and make better things. And I think we're lucky to have him here. He is in demand. He's frequently traveling across the world talking about these ideas and concepts. And he's today going to talk about some fundamental principles of design and how things are made and more recent advancements and usage of computational science tools and bridging of those tools to solve things that haven't been able to be solved. So please welcome Professor Liu.
Thank you very much, today. Remarkable talk, right? Great, thank you. And it's a great pleasure to be back here. I think it is my third time with the minds here. It's fantastic. I like this area, the air steamer in Pennsylvania. Very refreshing. Thank you, thank you. Okay, I'm talking about design. As you mentioned, my name is Zikui Liu. I've been at Penn State for 24 years now. I'm starting my 25th year at Penn State. I still enjoy it. I'm good. Great. So ask me, actually, talk about this a little bit broader. I was thinking called material design. Then I like to make it shorter, just move materials up. Again, you can design anything, right? Not only materials. I'm talking some students can design your career, design your life, design your family. And so the principles are applied. And we can take this apply today. I could see you, good to see you. Good to see you. We worked together. Yeah, you see with the project a long time ago, right? That was a long time. Okay. So I'm talking about design. Okay. So how to design? Question. I usually do not start with a question on my presentation. As you told me yesterday, I should start with questions. And he gave me a lot of very interesting kind of EDG. So I try it once, see how it works. Of course, we know that when design says you have to first define what you want to do, right? Design the desired performance. And then you have to go from here to there. You have to find out the combination of ingredients we're going to get and what the procedures. Okay? So this makes two things. To do that, where you're going to go, when you're here, you're going to connect the dots together. And then for material design is that as we know that we want to perform, and when we talk about performance, we talk about several properties, property and ductility and strength and so forth. So you first have to decide what the chemistry you want, right? Unique alloy, alumni, copper alloys, and add some elements into it. And then you have to find out how much can you put in there. Then you have to see how to the project, the forging, you can casting, you can edit, additive manufacturing, and so forth. And at the end of the day, you control microstructure. So that would differentiate us from the physics, from the chemists. We want a microstructure. And if you talk about the physicists that talk about the chemists, they don't know what the microstructure is. They know the molecules. If you talk about the green sites, they say, what's that? Right? You talk about they have a coherent interface. Never heard about it. Okay, that's since we have, which they don't have. I think that's why material science or engineering is so interesting because your playground is much bigger than other people have. All right, so then why is it challenging? Oh, it's good, right? We have to table together. So it's very, very challenging, as we show you next few slides, because there are multi-variables. There are too many variables. First one. Second is that, and we don't have enough knowledge to connect it. So, for example, you want to reduce the stacking point energy, or to increase stacking point energy, want to make it if it's coherent, or semi-coherent, or incoherent. Right? You want to make the green size very small or green size very big. So when do we want the green size very big? That's right. When do you want the grain size very small? We want more. There are different applications. Sometimes one big, sometimes small. It's not just a grain size big is better, right? People say do nano. But nano, yeah, sometimes good, but not very good, right? The people probably nano will be terrible. So, combination. So this is very, so we're lack of knowledge, or the information, or the data. Of course, then I think we have been designing, human has been designing materials for ages, right? Okay, but today we call it material science engineering. I would not call it material science engineering science. Okay? We'll do engineering first, with the science later. And this has been our history. So I design materials called I call it universal engineering design because I would want to go back inside. But I have been done for years, for generations, for millennials. And but now we've been smarter, right? So when they not only do that, want to design, what is the forward in this simulation? Want to say if you give aluminum copper together, tell me what the property. That's what we want, right? So we can take we change the copper from 5% to 10% of the difference. Is that better or worse? How do we have to do that? But how do we put it back together? If you think about it, from dynamics I've learned, you learn the Gibbs energy, you talk about the energy, you talk about the atomic mobility, microstructure. I highlighted this one word with individual phases and with the control. Time. We control with FCC, PCC, HSP, or the precipitates, or MC carbide, MCC carbide, whatever carbide you put in. Or large phase. We talk about sigma phase, the other phase we don't want it. You put them together, you see the individual phases. That's why back many years ago, in 2003 here, for the year 2003, for year actually in 2002, I decided that we should call all this materials genome. So I decided to call it material genome because it's building blocks, yeah, like you know, when you were young, you play Lego, right? And the building blocks. So the building blocks is basically genome for your toy. But for material science, we build up different phases. Because the nuclear alloy is FCC, steel is BCC, right? You got a bigger, bigger steel center here, right? It's most of BCC, but sometimes the FCC, right? You do FCC steel too. Okay? I control different factors. So that's why I call it building blocks of material genome. Okay, let's see how did human design materials? Human has been designing materials many years ago, right? So we design material, we say, you look at the history of the human. You see, we first use nature materials for nature stone waste, right? Because we don't know how to make material at the time. We just take the materials from nature, from the wood, from the bamboo, and so forth. And we this for many years. It took so long time for us to get used to the existing materials. Then we become smarter, right? Because we know we do that. So we do a bronze age, which is carbon 12%. Or 20 to 25%, around 3,500 or 300 BC. Ask you a question, why 12% tin? Can anybody tell me why 12%? Why not 11%? And why not 10%? And why not 30%? Google it. Yes. Sorry? For the war? Yeah. That's one fact. That's but people can change it. Yeah? People can change it. So what 20%? And also 25%, right? 12. There are two groups of grounds. We dig it out, we found that two different concentration, right? One 12%, one 25%. There's nothing between.
What's the reduction in melting temperature?
Okay, melting temperature is very important. That's very important. What else? Remember I mentioned the phases, right? This is phases control. Even though they didn't have phase diagram at that time, but we have phase diagram. They show phase diagram. This is carbon chain phase diagram. Okay, 12%. What's 12%? 12% is there. 25 is there. So why 12% now is clear, right? 12%, you can do the single phase region carbon at high temperature, around 1 degree C. So you don't have those a lot of intermetallic phase, make it brittle. Of course, they didn't have phase diagram, they have no thermodynamics, but they try to find the 12% the best. Anything else? We melt, change the composition, right? 12%. But 12% is single phase, a little bit of phase very low temperature, so it's not very strong, right? You want to make stronger, we gotta have intermediate phases. That's 20-25% the alloy. You have a lot of precipitates there. The metallurgist is age years old. It's 3,500 BC. The metallurgist is there already, okay? Of course, they have no phase diagrams, they cannot measure composition, but they know the property of it. That's this many years practice, they design this one. But the next one, the next age, we know is Iron Age, which mines is one of the best in the world doing that one. So it's set for 1200 BC and 800 AD. Okay. And a long time, 2,000 years. Of course, you know, the iron carbon phase diagram, right? So now you see it's more complex. It's not more complex than that one, right? It's simpler. You just have a gamma phase, alpha phase, and the cementite and graphite. It's simpler than the copper tin system. Right. It's way more complex. Which John says it's way more complex than copper tin. Why is that? Okay. Look at this structure here. This structure, at the top of the AB structure, is with same carbon concentration, same cooling rate, okay, but with a different oxidizing temperature. Look at the microstructure. Look at the phases. Properties is way completely different. Same chemistry, same cooling rate, just to change my green size a little bit at the beginning. The second one, the second bottom row is that the same carbon, it's same green size, but just change the cooling rate a little bit. Oh, that's the air core. What is the structure difference, right? The bond is different. So the iron carbon is way more complex than the bronze. That's why the iron carbon is discovered later because it's more complex. If you really want to look at the carbon phase diagram I showed you before, look at this diagram. So complex, just the two phases, not three phases. FCC, BC, and the cementite. Look at the given structure you get. By changing cooling rate, by changing green size. The playground is way, way big. That's why, you know, have you ever seen the blacksmith make something? They heat a piece of steel in the oven and take out a bit and put it back again. They decide, oh, maybe punch it, right? And put it back again. This is basically this kind of processing. They make the shape and heat up the arsenal, punch down. You could make different deformation, give you different green sizes. And then the good blacksmiths make a better product, right? Because they have more experience. That's knowledge and information that get an apprentice continuous go generation by generation. Okay. All right. So now you see that we become smarter, right? We get the industrial, industrial manufacturing materials 1.0 to 3.0. Okay, steam power, electricity, and computerization. Now we make it still better than better than before. I want to show you a graph here. How many of you know where this is? John knows that, okay. Anybody else? Yes, okay, Sumi knows that. Nobody still know that? This is the first iron bridge made in the world in Britain, next to Birmingham. At least that place is last summer. Do you know where it was built? I've got to put here the age. Well, I think it's just time here. Okay, industry revolution 1.0. I can show you. Can you see a date there? 1779. He's still working today. I walked on top of the bridge. 1777 bridge. Okay, you have to make maintenance and so forth, right? 1779. Just show the strength of steel we had. But today, now we're coming to the industry 4.0 is digitization. So remember I talked about the knowledge, right? Lack of, I said first is knowledge, then information, then data, right? So now we basically see this knowledge a period, like an information period. Now we're going to digitization. Okay. So this is the materials knowledge. With the knowledge that we know materials, we have to do two steps. Right? Before you have the chemistry, you have to get the manufacture, right? Get the phase stability. So first the manufacture. The process materials for multiple properties. You have to control the formation of the phases.
It might be good to adjust your microphone. It seems to have fallen.
Bigger?
Yeah.
Better?
Maybe the battery's
Oh, his battery's off. Yeah, no.
All right, switch it.
Yeah, switch down and off. No lights.
And you have to count on your Singing training.
So, okay. You hear me okay back here? All right. What does increase liquid now? And so controlled formation phases, you need to know is phase stability, right? Phase stability. The phase stability was dictated by thermodynamics. And you know that the thermodynamics started in 1700, it goes with the Industrial Revolution. Okay, kind of first law, second law, and so forth. In 1870, Gibbs formalized the thermodynamics. So Gibbs is the greatest scientist, American scientist. He's only one. So. The second one that.
Feynman.
Huh?
Feynman was the second.
Feynman was the second one. Okay. Did somebody say that?
What?
It was defined by as a second. Was it given the title as second one?
No. I'm just saying.
Oh, yes,
Feynman was also American scientist.
Was he the second best or the best?
Well, I don't know that. Depends who you ask.
I don't know. Gibbs was said to the best was Einstein said. Einstein said Gibbs was the best American scientist. The reason is because he made such a contribution, he combined the first and the second law. He made the combined law. However, he removed the second law from his law. So he's still back to the first. All right, anyway, so in 1970, 100 years later, Larry Kaufman, and he digitized the thermodynamics. I created the Kaplan model. He put the thermodynamics into equations. He can solve and create databases. I called him the digitization of thermodynamics. And today, in the world, most of the companies use the Kaplan databases for the materials calculation. If you know the name of the companies, they probably have a Kaplan database behind their work. The first example, how many of you have an Apple Watch? Quite a few hands. Okay. This is the Apple Watch came out in 2014. And they have been designed this for a long time, but they have tried to get the materials right. So you see that they have the steel, they have the stainless steel, they have the gold. This one was a failure, but not too expensive, right? Anyway, this is the chain, and this is the 7,000. 7,000 cannot make this case before. It's impossible. Apple hired some data scientists, including my wife, to design the satellite. Yes. Oh, thank you very much. Instead of 5 to 10 years, can you alloy? It took them 2 years and the problem is father. So sooner or later, I said to my wife, "It's smart thing, right? It's recorded." So this took 2 years to get this in the product, from design to product. Also, these steel 316L stainless steel, these alloys and the chemistries are different. So Apple does not need to follow the industry specification, it makes their own alloys. Okay. So one example, another example is this one, the nose at SpaceX. Let's put it up here. Okay, that's fine. The SpaceX and the Tesla is dual alloys. They have their own alloys. So they're great. If you know that the person leading both companies in terms of materials is a person called Charlie Kuhlman. Because my former boss at Questec, and he's VP for both companies' materials. So a lot of very interesting work. So have a database behind this kind of the approach. Okay, so as you probably know that in 2011, and the government decides materials is so important, they created the Material Genome Initiative, to kind of make a more systematic material design. Basically, define the should put another here. All right. Yeah. So basically make it develop faster, and save time and save money, and even develop the national security and those get the people for like you for students. And it really emphasized here, as you can see, is that it's the database, is data. The data is true. I need the general raw data. That's computation to an experiment to all the data. At the end of the data. The data is the knowledge, information. Okay, in my group, so I came to Princeton 98, 99. Then I took over the Kafka community, a organizational work and a journal. So we developed data generation tools. We do machine learning, we do DFT calculations, and we compile experiment data, we make databases. And then we have to process this data in the databases. Use to develop open source codes to do the data processing, PyCarta, SBase, and those uncertainty codification. Industry always asks us, you can't face the transient temperature. What is the uncertainty in that temperature? Now we can do it. Okay, next I think it's like maybe a plus minus 20 degree, a 95% range. We can have the exact number on that. And then we wanted to train get more people involved, so we created a nonprofit foundation, Magic Geno Foundation, and we are now doing a broken open source ecosystem for material science, OSMEX. We just get a funding to do that through Penn State and Foundation, nonprofit foundation. So if you guys do any programming, you would like to collaborate with us, we'd be happy to put your code on the platform and also doing the training courses, happy to do the workshops and our open source. All right, so as I mentioned the other day, we can generate from experiments from DFT. It's all faster and faster, but into machine learning is the fastest. So they're working on machine learning, and we have now have actually released this one open source now. If you have Cyclopen or PyCyclopen, and then you will get this data. You can download it, install it on your computer. Predict the formation energy at 0 Kelvin. The basic part of DFT. So you can do machine learning first, and then DFT later to validate it. Our next one we come out is the free energy prediction. We have entropy that too. Hopefully next year, the students graduates have the free energy model. And also you got the data, you can do simulation and intuition and design chemistry. Right? And most people do have the knowledge, you have this chemistry with calculation. That's called forward simulation. And in my one you must design. So we got a new project, and we project anymore. In 2021, we had a project from Hawaii to do the inverse design, CGAN, conditional generating adversely networks. We had a new faculty on that, so now we have the inverse design platform. It's not open source yet because we haven't fully completed. Hopefully by this year or early next year, we can open source code for the inverse design. So we're going to 4th cycle now, right? The difference between this CGAN in the traditional machine learning is that most machine is forward. Okay? So we want to go back. So you need 2 machine learning models, basically. One go forward, one go back, put them together. I'm not the expert on that, but I have a collaborator. If you're interested, we'll be more than welcome to look into it, and we will collaborate with you. We have created the largest refractory high value database. We have 6,000 entries. What's next? So we can actually sit down. So we're going to finish my job and go click off. This is Professor John Spear somewhere. Right, what's next? Okay, what's next? I can say for the day we are trying to do. So we started simple because we can everything kind of find out 10 years ago. I think what's next to do, right? So 2008. I tell my student, we got to ask them, what's next? So we decided to have a retreat. So I tell my student that day, I'm like 10 students at that time, I said, let's define 5 topics we think is a big star challenge to us in science in general. Yeah. Can we solve it or not, right? Okay. Actually, we defined 4 and then we solved 3 already. Or we are solving 3 at one with different kinds of transparent materials. We'll work on that again. Okay, so at that time we actually find 2010, right? 2010, you know. This is the internet. Everybody knows that for water. This is the y-axis is the specific volume, basically molar volume. The x-axis is the temperature. So water is natural material, right? We need to make it is natural material. And this material is very interesting. I want to the temperature goes down, water decreases, right? Okay. But if you go down below 3.6 or 4 degrees Celsius, the water starts to go back and increase again. So that's called a negative sum expansion. So that's what I say this is the material is made by God. Right? God made that material. So that material is so special, it changes some expansion sign around 4 degrees C. Everybody knows why? It's not solved here. I'm saying again. And then in 1897, it's a professor, it's a scientist in Switzerland, he discovered Yingba alloy. How many of you have heard of Yingba? Okay, about half of you. So I have another here, Yingba. So Yingba is this one. Well, this is not exactly Yingba, he discovered was iron nickel. But iron nickel is too complicated. Calculus would iron 3 platinum. Platinum magnetic. So this is the same diagram. This is a linear sum expansion. It's just like volume, you can think about this one. And the function of temperature, derivative volume. There's some expansion increases, right? It's normal. Then there's the material side T, and time of increase and decrease my volume. Then some to the negative increase. Okay, then go back again. Okay? This Einstein has some mind, his own mind. He said, I'm not following people who believe the body can increase with temperature. It's man-made material. So then materialize people will say, we know everything now. We can we predict it. Can we predict this mechanism? When you say, of course, we did. Otherwise, I will not tell the story, right? So symbols on this line, and this diagram is from experiments. The line is from prediction, without a fitting parameter, without even model for some expansion. All right. So this kind of behavior people call it emergent behavior. Okay. And then they say, oh, this is purely discovered by chance, right? Not by design. And then my question, can we predict on quantum mechanics? Because I get quantum mechanics guy in my group, I say, people know hard work to do. Of course, this is very successful. So what does it mean? Oh, this is one problem. The next one was I presented yesterday, Tuesday, and they had the Sharp Mega organized. Wonderful event. It's my first time to Fermi Lecture Conference. So this is one of the traditional lines that terminate. The y-axis is the next parameter, and the x-axis is temperature. You see, at low temperature have CA ratio, that's tetragonal, right? Tetragonal polarization too. Then the titanium is displaced from the center. And if you go to high temperature now, you see C equal A, then it says cubic. But that's, I get a transformation from tetragonal cubic based on my experiment. Okay. Low temperature tetragonal with polarization, and high temperature cubic. Perfect. But there's always some scientists that say this is not quite accurate here. So in 1994, there was one scientist that measured they use X-star to measure titanium environment. So what they found is that, so you get the lines here from the X-rays as should before, but the symbols is cross the symbols, and this diameter is from these X-star measurements. So titanium never goes to center. And it's always at the tetragonal position. Okay. And then the next is also tetragonal. And then you measure the polarization too. You find that the titanium is always displaced. Not only tetragonal, but also polarized. So that means if you do X-ray, neutral, you find it's not polarized, it is cubic. If you do X-sub, it's polarized, it's tetragonal. Which one's right? What do you think?
Both.
Sorry?
Both.
Both, of course, both. Why both are correct? Why both are correct? And you find experiments, right? You cannot argue with experiments. They're correct. Okay. That's not happening before. But the community always keep on believing. The general community keep on believing it's non-tetragonal, it's cubic and non-polarized. Today, you talk about how 50% of people still think it's a cubic non-polarized. I don't understand why they do that. I'm sure they have good reasons, but I don't know. Okay. So it's really the probability issue. Okay. You have learned this statistical mechanics, right? It's that function with summation, first words, you do the probability, you do the energy, you do it. Right? It's standard. Questions, but it's not no question about it. Okay. And then you say, and so if you suppose the system only have one configuration. What you expect? That means only one, that is F equal to EK, right? and EK, but if EK minus SK, so SK must equal 0, right? So that means you have one contribution system has no entropy. What does that mean? If the system is not entropy, that means it's pure quantum state. The only quantum state, quantum state. It doesn't change. Okay? But however, all the systems we deal with are not pure quantum state. So it means these equations we have been talking in the class, it's not applicable. Well, it's correct, but it's not applicable to anything we deal with, except it is pure quantum state, but we don't have pure quantum state. So I have been teaching this one for years, still teach every day in the world, and it's not useful. How about that? But everybody uses it. It's not useful, everybody uses it means it's wrong application, right? That is using it wrong, so to speak. So how can we make it correct? I hope we can do that correct. All right, so I want to show a movie. So how many of you know this one? KG, a summer tour. Everyone knows it, right? Okay, I'm going to play the movie. I can play movie here. Let me see if I can do that. After this, actually works, okay? No, it doesn't. So you can play here. So this is the paper card. I have two sides. One side is cage, and another side is bird. Right? Okay, if you're going to start to spin it, is a cage, bird, cage, bird, what do you see? It's like, now you see, bird in the cage. Right? So you have bird, cage, bird in the cage. So we know it's correct. It's bird, cage, correct, or bird in the cage, correct. What's the correct? What's the correct, right? What's the correct? The bird cage separate is correct. Bird in the cage is also correct. So it depends on your resolution. If your eye is as fast as spin, you see bird in the cage. If you're tired, your eye doesn't react so fast, you see bird in the cage. So both are correct. If your observation. Something like that one. Like the left-handed. If your X-ray is not fast enough, you see cubic. If your X-ray is so fast, you see triangle. That makes sense? It's statistical. All right. So when it comes to statistical, quantum mechanics, Einstein said that God does not play dice with the universe. It is because he didn't believe quantum mechanics. Because he doesn't relativity, quantum mechanics is uncertain, right? He liked to be certain, not uncertain. He said it cannot be uncertain. The universe must be certain. Okay, but this is really because it becomes stochastic or deterministic. Is the universe statistical or stochastic or deterministic? Both. Okay, depends on your resolution. Okay, so as I was saying about that. All right, so let's look at statistics again. What does it mean? What it means is that in a system, we have a lot of different configurations. Okay. So that means each configuration has a probability to be observed. So N should be equal to minus KB, summation of peak log decay. So that was actually derived by Gibbs. But we don't realize that because Gibbs has collected works at two volumes, volume 1 and volume 2. We always look at volume 1, forget volume 2. But volume 2 is statistical. Actually, I think it would be very hard for anybody to catch Gibbs as the best scientist because he does thermodynamics, he did statistics. Most people just do one thing, right? He did two things. All right. So let's call it a top-down approach. Look down here, the system still have some configurations, right? But however, if each configuration has some entropy, right? So if each configuration is not a pure quantum state, it has entropy. So what does the total entropy look like? So we have like 50 people here, right? So we have different configurations, like configuration entropy, but each person brings entropy in the system, right? So the total entropy will be everybody together, then the configuration entropy. This. So instead of one term of the standard certificate, we should add one more term. That's the contribution of each configuration has its own entropy. Of course, the agency one of each of them has its own entropy down there, right? You can always go down, go down, go down, go down the P1 state. But at the moment, we can't go down the P1 state, we can go down the electrons by DFT. The quantum mechanics was discovered in the 1920s, but it's no use, no practical use for until 1964, when the DFT was discovered. So now this is going to bottom up. We can start with the electron, and then we can statistics we can put together. We have been using this method for many years, and in 2021 we gave a talk to Virtual Talk. But it's going to virtual is going to many people from different places that come together. So come with an approach. I said we don't have a name for our approach. We should call it what we should call it. We have different ways. Think about the names. We can multi-scale entropy, right? There's one postdoc is so creative. And he raised his hand. He said, we should call it entropy. I said, why is entropy? He said, because you use partition function Z, right? Partition function Z. Okay? And then you're talking about different scale of entropy. You're stacking them up. So Z partition function in German is substance sum, means the summation of states. So you're doing summation of entropy, essentially is perfect. So we are convinced. So we now call it entropy. All right. So we know that the Boltzmann density function theory is talking about 0 Kelvin, 1994, 96, 165. We did the series. So it's about ground state. But most of people do not know the phonon. Some electron. Actually, turned out that the electrons was down in 1964 already by that paper. But when they introduced the density function theory, they had some electron contribute for energy. Okay? But they didn't phonon at that time. So chips have the phonon. So you actually can calculate the energy of that configuration. But we just mentioned we have so many different configurations, and not just one configuration, so we calculate all other configurations too. That's it. So we need to calculate all possible configurations, put them back together. Then you get the entropy of each configuration. Now you get all configurations, you get all energy, put them back. You can predict the energy of the system, which is entropy. So you have to modify the partition function. So what I modify is that we call it entropy because since you have three terms now, two terms. One is from the quantum mechanics, another from statistical mechanics, and another from thermodynamic measurements. It does not give. You measure heat capacity, you measure entropy by measure heat capacity integration. This one. So if you do this one, you get a energy. Oh, I'm just telling you. Oh, that's the equation here. Okay. And just go back a little bit. Oh, actually a French term. I deleted French. Okay, I got French term. All right. So we go back to the problem we had. This problem we had, right? This is iron sweep diagram. We know iron is magnetic. Okay, iron has spins. And usually you take the spin up, spin down, Ising model. You take the collinear Ising model. So if you take how many ions, each ion has spin up, spin down, so 2 to the n power of the configurations, right? If you have three, you have nine, you have three ion atoms, then 2 to the 3 power will be 8 configurations, right? But that's very small. So you make it bigger. You make it have 9 ion atoms. The 2 to 9 power will give us a 512 configurations. But if you have symmetry, there will be 30 some of them are unique. Okay? So now by 512 spin configurations of 37 unique ones, then we calculate the energy at 0 Kelvin. It's energy as function volume. That's standard DFT, very fast calculate them. And as I mentioned, we calculate energy, right? I can energy of all configurations at the same of them. The interesting is that this is reference to the ground state. The ground state, you can see that if you purify the energy, you achieve no transition at all, right? And the lowest energy based on some of the names, no energy, no transformation. However, because the probability, statistical is beyond the static. So you put a statistic on top of that one, you find that at the 0 Kelvin, it's 100% is one state, but when temperature increases, the population of the one state decrease, it even go below 50%. Even though it's energy state the lowest. But it's 1 against the 510. You lose the game. Okay. Even though your energy is lowest, but it's overwhelmed by other configurations. The number of places will be. So you see that at a certain temperature, which we define as critical temperature, the majority becomes the minority, below 50%. And then we can predict that the temperature as function of apparent temperature, right? That we see here. You see, actually around this area is already, the volume is not increased much anymore. At some temperature becomes negative. We come back. So why would the volume decrease at that time? At the temperature rate. Look at this one. All the metastable ones have a smaller volume, right? The ones that has larger volume, right? So all the replacements have smaller volume. So everybody will have volume increase, but the replacement rates is larger than the volume increase rates, the total volume can decrease. So it's nothing strange. Actually, nothing wrong about this software modes. It's basically replacement. It's a number game. But at the end, because this replacement doesn't change much anymore, right? But everyone's positive some expression, so it's just a positive back positive. So we can give the pressure, so we get a PT diagram. So again, the line is the prediction and the symbols are for experiments. No fitting, no model, right? No model. Purely DFT plus statistical mechanics. No model, no fitting. I think that prediction, I'm happy with that prediction. I did a great job. But that's not enough here. The most important is that then you see that it's a critical point here. You know what the critical point, right? Critical point is that the physical property diverges. That means some experiment goes to infinity. Okay? So how do we cannot see some experiment this one, but if we change the pressure to volume, then we see some expansion. This diagram here. So we change the pressure to volume, and then each line is for the isopressure curve, isomorphic curve. So the black dots here are experiment data, just like here, okay, but not some expression of the volume. The volume, the technical sample first increase, and then say, oh, I'm going to increase less now, and then at the proper point, say I'm going to decrease, and then increase again. So each pressure is a band. So you see this band here, it's negative some expansion. At the critical point, the surface is negative infinity, right? Horizontal line. So that's what is the thermodynamic criteria when the physical property diverges. That's you can define it by calculation without this kind. That's the definition of the stability. All right. So go back to this problem. This problem have is that this one here. Oh, that's right. Yeah. So this is that the 753 is right at the transition temperature on the Technology cubic by X-ray. So we fix the shape, the white circle, white cubic from the experiment data. The last parameter, right? So then you heat it up to 753, and then you see the atoms here. The blue atoms are the titanium ion in the middle. You see, when you see the blue atom, that is a moves up, right? Move down, and move. Of course, it looks very slow, but actually very, very fast. We just the time, the 5 per second. Okay. Interesting that you don't see the blue atom sitting in the middle, right? It goes up and down, it goes to the sideways and so forth. So what it means is that, oh, stop moving. So you see that what happens is the atom starts to move in this direction, then go that way, go this way, so it's upside down. It's move all the time. So that means at a high temperature, you see it move very fast. In low temperature, it moves slow. Speed becomes slow. If you go to 0 Kelvin, it doesn't speed anymore. The computer dragon polarized. Then we started, if we put all these numbers together, compared with the experiments. So this is again the last parameters are from the temperature. You see the black lines, the dots are from the X-ray. Cubic, triangular, cubic, right? Okay. When you look at the X stuff, The blue lines here, it's like this, always tetragonal. Look at the simulation with the red line, it's always tetragonal. But it is cubic, you see, when the atom goes like this, when it goes before it goes like that, have to go to the center point, that's actually cubic. So to have some time that cubic, most times it's tetragonal. So we put a height on that. You look at the polarization, same thing. You get neutron X-ray give you non-polarization of the transient temperature, and you look at the individual titanium atoms is always displaced. So that's good one is your resolution. If you are slow, it's cubic. Fast, it's tetragonal. So both are correct. But the question is, can we predict it, right? So we can predict it. Like we see next. So we have to figure out what configuration we have. So you think about if at 0 Kelvin, all the polarization lines up, you get one ferroelectric configuration. Okay. And when one goes to this one, you get 90 degree, right? They call 90 degree domain one. Okay. If the titanium goes out direction, you get 180 degree domain. The total are the only 3 configurations possible. Okay, first the ferroelectric, the second one is 90 degree domain one, 180 degree. Only 3 configurations from this complex structure. But of course, you have to use symbolic multiplicity. The first one is tetragonal, ferroelectric. Second one is the top one is 180 degree. Speed, the polarization is up and down. And the C is 90 degrees, it comes in, it's out. The degree is 90 degrees in the polarization direction. So, of course, this is the interesting people are calculating already. They calculate the energy, domain one energy. Of course, different literature calculation will be different. So we take 2 sets of data and take this data is we believe this data is more accurate, even though it's older data. We take the data, we predict the transition temperature 773.6 and experiment 763. Okay. Again, it's no fitting in the model, even do that model, but you have to get a configuration. But if you take this data, it gets below temperature. This 100 degree, 120 degree off. This is like a 16, 17 degree off. We understand why this data is better. Because this data is interesting. This data did not relax the super system. And this is relaxed. Usually relax is better, right? The calculation. But this case is wrong. If you do the statistical mechanics, you cannot relax. We talk about that in the next slide. And then we can predict the entropy. The entropy is very, very huge, in fact. 1.5 kb is huge. It's kind of crazy. All right, so I want to just stop my talk here now. Is that I want to mention to you, if you get some dynamics, you can get all kinds of properties. Okay, most of the properties are secondary derivative of the free energy. It's the first derivative between the potentials and the molar quantities. For the heat capacity, this kind of properties, permittivity, and elastic compliance. And those that in the diagonals must be always positive for stable system. That's just by definition of stability. However, the off-diagonal terms are between the long-conjugated variables. They can be either positive or negative. That's why some splits are positive, negative. Of the all other properties. I was the confidence of the field, you talk about the negative Pearson's effect. Pearson's electric effect, of course, negative. It's here. Okay, it has like some expression. It's actually the same quantity because they're equal. Because they're based on Maxwell relation. So Pearson's caloric effect, it just makes some expression. So this is very good. We can predict a lot of properties now. And the last few years, I was getting involved with the kinetics. They talk about the cross phenomenon. Then we found another set of parameters, which is never talked about in the literature. It's the derivative between 2 potentials. Okay. So for example, how about the stress to temperature derivative? Okay. Electric field to temperature derivative. We found this property is actually extremely useful to us. For example, something electric, Seebeck coefficient. Seebeck coefficient, people always think is the kinetic properties. Okay, people use kinetic methods to calculate. Turns out when Seebeck coefficient, Seebeck coefficient is this one here, is the chemical potential of electron to temperature derivative. That's Seebeck coefficient. So we get this idea, we published 2 papers, so we predicted the super coefficient without Boltzmann method. All right, with that one, I want to give summary here. Design is multi-scale hierarchical structures. Okay, you can do empirical, maybe you can do that. You can do national, maybe do inverse design. This is machine. Nice. Building blocks also are multi-scale. You can start with the electron, go to atoms, go to chemistry, go to microstructure. You can do all different building blocks as that. So when in 2002, when I said material genome, I'm talking about the base scale. Okay. And then now after the last 20 years, now we're moving down to this atomic scale, and now we're moving to electron scale. That is all based on quantum mechanics. And then we are going to the entropy drives all changes. I want to mention that the entropy theory represents the cross-screening of entropy from scale of electrons. And it combines the DFT with revised statistical mechanics. It can be transformed in practice. It can add the design of it. Thank you very much.
We have time for questions. Zikwe will also be here tomorrow for some time if you have follow-on questions. Faculty or students, fire away.
We talked a lot about time resolution, but what about spatial resolution?
Yeah, it's the same thing. You have to really see about that. But the question people always ask me, do you have to calculate your size is small, right? You need big size. Okay. My argument is that you do not need it. Okay. Unless you need your interaction is very long range. For example, in polarization case, you probably need it. But we just demonstrated you don't need it. But I think but the large scale structure is more complex. It's because you have so many more fluctuations, probability. You can form patterns. Okay, but it's just large scale fluctuation. So if you want to predict large scale fluctuation, of course, you have to do a large scale simulation. But if you only worry about the properties, you don't need that. So it depends on what property against scale.
So following up on that and going back to your slides on iron platinum.
Okay.
Did I understand correctly that you used just 9-spin supercell to?
12 atoms, 9 iron, 3 platinum.
Okay, and then you had 9 spins, pretty much. All right.
We get all experimental observations.
And then in your statistical mechanics treatment, are you what kind of energies are you putting? The energy of the entire cell?
Energy of configuration.
No, but per,
Not for more. It should be per supercell.
per supercell. So then if you triple the supercell, you have higher energy difference.
So
correct?
that's right. It actually is a great question. You do not want to get more configurations. Balance it.
No, but if you have the same two configurations,
No, no.
but you triple the unit cell,
That's
the
right.
energy difference triples.
That's right.
Then your temperature is different.
No, your number of configurations has to be changed too.
Agreed.
Previously you have a 512 configuration. Now you double the size of it. You double the size of so be 500 times 512 configuration. So at the end of the day, you get the same results. That's actually a great question. So that's actually even more important is that size doesn't matter. Yes.
So the simulation cell sizes, if you're calculating like bonon modes, do you have to worry about losing the long wavelength acoustic mode distribution?
That's a great question. That's actually extremely important. So it's important that your tube cell calculate. For example, the domain wall, right? We will have our interaction. So you have to change your size. Actually, they did already. We didn't have to do that. You have to change your cell size until the domain wall energy does not change anymore. That means you move the interaction between domain walls. That's the key. If you make smaller, it's not going to right. But for magnetic, it's different. Magnetic phase is always still original. Okay. If you take 9 atoms, they're all big enough. That's big difference between the ferroelectric and ferromagnetic. That's actually, but it's a very important thing that when you do the statistical mechanics, every configuration must have the same volume, not the minimum energy of themselves. Because the errors can be constrained to the same model. Final model. If you take individual one, you result in
Any student questions?
yeah, it's the student. The student, sorry.
You try any simulations of any effects and how that could add to the entropy at higher temperatures?
We have not done particularly that. We try to do proposals for the radiation damage. They didn't give us money, so we didn't do it. But if anybody wants to do it, we will have to do that. But we did the vacancy information. Then we did a specific prediction. And it's beautiful. Yeah, it's unbelievable. When we first get a paper, we were surprised. The diffusivity is in the experimental error bar range. Of course, you have to give the correlation function, functionals, you have to correlation function, you have to find different settings, so forth, right? But with this AEB, that's it works perfect. Very nice. And actually today, most of people doing this the diffusive calculations use method we developed back in 2000.
I'll ask you questions, quick. So lots of students and faculty here do work related to processing. And the question that the student had, that introduces variables that take the material away from its fundamental grounds. If you look at impactful work, oftentimes it goes to not the fundamental behavior of the material, but the processing of the material. So I guess philosophically, how far are we away from using ground up inverse design to be able to inform how to take a top down approach and actually make it in that predicted state?
Great, that's an excellent what we want to make it useful. That's our latest project from APAE is to inverse design high trivial as five terms applications. Okay. So what we did is that we collect all data from the literature. Of course, it's way incomplete, right? That's big data points for its multi-column space. So I have to generate all the data by ourselves. So we don't have the apparatus, so we develop a quick model generate data from our DFT machine learning. Very quickly generate we call synthetic data. Then we do inverse design that data. Then we can do experiments, right? That's what we're doing now. My next thing to do is that when you do the manufacturing process, you go to barrier. So the barrier is one of the important thing because you have to decide how much force to apply to local barrier, right? So barrier predicts it very hard. But it turns out Lazintre can predict barrier. You can predict the barrier from one state to another state without a problem of instability. Without a problem of the imaginary formula, because we don't do the formula for the imaginary state. It's a mixture of different states actually create the barrier. So I think that's actually the next thing is that one develops the energy landscape. So you can, if on your system process problem, you can decide which path to go. So we can give you these directions.
John, and then James.
The first thing, thanks for your presentation. So earlier in the talk, you showed some sort of iron carbon ferrite pearlite microstructures and a diagram that showed microstructure development. And so you had some different ferrite with different morphologies. And so I guess my question is, how long do you think it'll be before we could, predict everything that you see in this slide from first principles?
I'm a very optimistic person. But I started this, I was not a mature scientist in my undergrad study. I was doing iron making as my major. Actually, before I'm making, if I'm making, you have to do pellets, right? So the concentrated powder, make the pellets, put in the blast furnace. So my undergrad study was how to make the best pellets to put in the blast furnace. So when I was junior class, a lady can give a talk about the heat treatment. We were talking about the Bain transition. we talk about the argument between the two community, the two domains of people. One is the displacing, one is the introducing, right? And they cannot solve problem. I said, I'm going to solve the problem. So children major. I went to school, I went to start face transformation. I look at the channel who does face transformation, and USTD does face transformation. So I went to USP again, my other guys, the guys in that study. So I did a lot of experiments on the brain actions. That's my project. I want to do that one, it could be kind of for that. But today, I think it's still not fully resolved. But I think its message is there now. Okay. The reason is because I first made a Nochin Chen, Japan State, you know that, in 1994, when I came to the United States for a conference. He presented the face transformation, face simulation. I said, that's the way to go. So basically, face field. So however, that's 20 some years now, right? That's 30 years now. 94, they said, so why is it not there? Why the face field simulations are not to be able to show this one accurately? It's good as experiment. Of course, this is just one snapshot. It's statistical. Okay, because many of them are different, right? So I guess can you get the features correct? I think the actual face field is there already, message is there already. It's the data you put in. So you need a very good thermodynamic database, a very good diffusion database, you need a very good energy landscape. So I think with what we have now, which we haven't done this still yet, but I think with the we're developing, we can put them together. Maybe we can do, I think for iron carbon, we'll do binary system, right? Iron carbon, just to this condition, I think it will be, we should be able to generate almost the exact structure.
Yeah, although there's a, nucleation crystallography
That's
and
right.
all of the interface.
That's right.
So it's-
Still resolve when they're putting together. I think maybe you can write a proposal together.
My next lifetime.
Get 2 grad students, come to the FT, want to face field simulation, I get 3, that's the experiments. And we can get work in 3 years. Yeah, I think the method is there. Okay, just we need this teams putting together. Because there's so many problems to address, right? And this is one problem. One of the problems. Probably low priority in the funding agency side. But your center is so big, we can just get a price here. I'm ready to do that.
If we're past time, if people have to go for it, but James had a question, so we'll hold it up.
So I'm not just saying this to make you guys happy. So Dr. Spear actually took my question. Had a great answer.
Okay,
I don't have any.
I'm sorry.
Okay,